Perfect. Awesome. All right. So let's make a start. First of all, I would like to thank you for inviting me to your group. I'm really excited to be joining you tonight. My name is Patrick. I'm the mobile chapter lead at Flybys. I organize the Melbourne TensorFlow user group, and I'm an active member of the TensorFlow JS and the TensorFlow Lite working groups at Google. Tonight, I'm going to talk to you about how can you go from knowing very little or nothing about machine learning to seeing how it works for a computer vision scenario. There's so much discussion about machine learning, and with so much information, it's very confusing. So I want to boil it down to some of the essentials, show you how it works, and maybe help you get started on the road to becoming a machine learning developer. It's actually much easier than what you may think. Before we start, let's try and get some clarification on all the buzzwords that we hear these days. What is the difference between artificial intelligence, machine learning, or deep learning? AI is normally defined as human intelligence exhibited by machines, but that's probably a very broad term, and it is currently changing a little bit and evolving. Most commonly today, we work with narrow AI, where a system can do just one of or a few defined things as well or better than humans, like recognizing objects we trained it to learn. A typical example would be in the medical industry, where doctors use AI to analyze images of patient scans to detect any issues, and they can do that with increased speed and accuracy. Then we have machine learning. This is where the actual implementation takes place through coding and analysis of the data in order to produce an application that can classify previously unseen examples. And that application is actually reusable. So for example, if we build a system that recognizes cats, we could be able to use it to recognize dogs without changing its core implementation. And here are some of the common use cases for machine learning. We have object detection, where we recognize an object from an image. Regression, which basically means predicting a numerical value from some other input. And we'll see an example of both today. Then we have natural language processing, which allows us to interpret sentiment or meaning from a phrase. For example, we could detect whether a comment in an online blog is toxic or has a negative statement. Speech recognition is probably something that I imagine most of you use on your phones with voice assistants like Siri and Google. And finally, we have generative or creative examples like the one we see on the slide. Deep learning itself is a technique that we can use to create a machine learning program that we just talked about before. Think of this as the most common algorithm that you can use to train a model for the data that we currently have. So to summarize, deep learning is a technique that drives machine learning, which then itself enables us, like the entire field of artificial intelligence. Let's take a look at the traditional software development at the moment, but add some labels, for some of the artifacts. For example, you've probably seen code like this, where you read in some data, perform some manipulations on the data, and you return the result. It's what we normally do in the software industry. Or maybe you've seen code like this in a game, where you want to determine the behavior of the game, how to move the ball, what happens when it collides with the brick, and etc. So traditional programming could be summarized in a graph like this. You express rules using code, act on the data, and you get back the answers. That's really pretty much like describes the common programming that we've been doing our whole careers. The machine learning revolution is just a new way of looking at this graph because it's a different methodology for coding. Instead of trying to figure out the rules ourselves and express them in code, what if we give the answers and the data and have the computer figure out what the rules are? That's the core of the entire machine learning revolution. It may not make too much sense right now, but we'll explore it in an example soon. Consider something like activity recognition. You may want to write an app that uses sensors on the phone or on a smartwatch or something else to determine the person's activity. You could, for example, use the data of the speed and write a rule that determines if the speed is below a certain amount that they're walking. And then you can extend it and say, okay, if if the speed is below 4, they're walking, otherwise they're running. It will work. You can go even further and say, okay, if the speed is below 4, they're working. Otherwise, if it's below, otherwise they're running. Otherwise, if it's below 12, they're biking. But how would you handle something like golfing? Like, what rules could you potentially write to determine that they're playing golf? Also, probably by now you kind of like realize that the other rules are a little bit naive as well. You can't just go by speed. You might be, going downhill faster, or you may be riding your bike slow. So let's go back to the original diagram and think about how machine learning could solve the problem. We can't figure out the rules for golfing, and our rules for the others are naive. So we can use machine learning. What if we give it answers and data and have a computer figure out the rules? So for example, it could look like this. We could consider all the sensors from the devices and grab the data when the users are doing the activity. We then label the data with something like walking, running, biking, and golfing. Now our problem becomes, can we match this data to the label? Like here, for example, maybe these parts of the data are always present when someone is doing a respective activity. And these values are always different when we're running, biking, or golfing, etc. Can we have a machine learning spot these patterns? And when it does spot them, can we then use whatever rules it figure out itself to determine which patterns match which labels? And have it look at future data as well to determine what activity we're performing. So how do we write a program to do that pattern matching? The process is actually quite simple. We'll start by making a guess as to the relationship between the data and the labels. Then we'll look all over our data and compare the guesses with the correct answers. We have those answers because we labeled them before. Then, based on the parameters of our guess and the accuracy that we got by measuring against the real answers, we have some data that will let us optimize our guess. And then we repeat until we make the result better and better. Tools like, like we're going to talk about, like TensorFlow and relative APIs, make that really easy for us to handle. So now if we go back to our diagram, the idea behind machine learning is to feed in the answers and the data and have the machine figure out the rules. And when we do this, we actually get a model. The model can then take the data and apply the pattern that it learned to match the data to answers to give us predictions for or an inference. So in our case, for the activity detection, now someone else could take a device and based on the pattern matching that we designed, figure out if the user is walking, biking, running, or golfing. Let's take a simple hello world example to see how we can put things together. We have a set of numbers here. Can you see the relationship between them? How do I get a y from x? I'll give you a couple of minutes if anyone is willing to try and take a guess. Okay, I'll give it away. Like I know it's Friday afternoon and things are a little bit tiring, but the formula is the y is 2 times the x minus 1. So for example, in the case of 2 times 2 is 4 minus 1 gives you 3, right? How do we actually go about to figure out that ourselves? We start doing that kind of like testing into our own brains, right? We essentially, creating ourselves as a machine learning classifier for solving that problem. So let's see how we would do that in a neural network. So here's an example of a TensorFlow app that will figure out that relationship for us. I know there's a lot of new concepts here, so I'll unpack them one by one. And I believe you feel a little bit comfortable with Python, so it doesn't look way too strange. First is this line, and actually this is probably the most mysterious of the bunch. So let's try and explain it a little bit visually. You often see pictures like this, of a neural network. Each of the columns in the red boxes here are called layers. And each of the blue dots are neurons. Every neuron is connected to every other neuron, and that's collected a dense layer because of the dense connectivity between them. You define this kind of neural networks using code. So let's go back to the code and see what we've defined. The first part of the line says it's a keras, sequential. Keras is just a framework within TensorFlow for making definition of training a model. We'll be using that a little bit further down in the workshop, so it will become a little bit more clear. The name sequential basically tells us that we're going to define a sequence of layers. In the diagram earlier, we had 3 layers. How many layers do you think are in the network we're going to define in this code? Right. Okay, the answer to this one is actually 1. Because we only have 1 line of code within the sequential. Notice what type of layer it is. It is a dense layer, which is the simplest layer type there is in the basic neurons in them. Later, we'll do something a bit more sophisticated, but dense layers are actually the most simple one. So we have 1 unit, and then that's visible within the dense parameters, and then we say we only have 1 unit or 1 neuron basically in this layer. That the input shape parameters tells us the shape of the data we train this layer on, and it's just 1. So our neural network essentially looks just like this. It is 1 layer with 1 neuron, and what the neuron can do is learn to match data to labels. So let's see how we're going to do that by returning to our code. It's literally the world's simplest neural network. You've probably seen that, and we were talking a little bit about it earlier, that for machine learning, you need to know a lot of math, calculus, probability, and the like. It's good to understand that as you want to optimize your models. But the nice thing about TensorFlow and Keras is that a lot of the math is implemented for you in functions. There are 2 function roles you should be aware though, and they are loss functions and the optimizers. This code defines them. Think about it this way. The neural network has no idea of the relationship between x and y. So it makes a guess. Say it guesses x equals 10 times, y equals 10 times x minus 10. It will then use the data that it knows about, the labels that we provided, to measure how good or bad that guess was. The loss function measures that. It then gives the data back to the optimizer, which figures out the next guess. So the logic is that each guess should be better than the one before. As the guesses get better and better, and the accuracy approaches 100%, the term convergence is used. So in this case, the loss is mean squared error, and the optimizer is SGD, which stands for stochastic gradient descent. If you want to learn more about this particular function as well as other options that may be better, check out the TensorFlow documentation. But for now, we're just going to use those. So our next step is to represent the known data. There are the x's and the y's we saw earlier. The NP array is using Python to call NumPy to create an array of those values. So we have one list for the x's and one list for the y's. Training takes place on the fit command. Here is what we're asking the model to figure out how to fit the x values to the y values. The epochs equals 500 value means that it will go through the training loop 500 times. So it will try to make a guess, like 1, 2, until it reaches the 500 iterations that we code. When the model has finished training, you can have it give you back values using the predict method. So it hasn't previously seen 10 because it wasn't in our list of code above. So what do you think it will return when we pass to 10? Any ideas? Our initial formula, remember, it was 2 times x minus 1. So if we give it an x value of 10, it should give us 19. Yep, that's right. So in theory, it should, right? But if you try this, and we'll try it ourselves in the next, like in the next little workshop, you'll see that it will return a value very close to 19, but not exactly 19. But what do you think that is? It's ultimately because of 2 main reasons. The first is that we trained it with very little data. We only gave it 6 values in its array, right? But in doing so, there is no real guarantee that the relationship will always be the same. But it's a high probability that will be something close to 19. So give me an opportunity to stop talking and maybe get our hands dirty a little bit with, you know, like with a hands-on workshop. So I've created have you used Jupyter notebooks before? I know you've studied a little bit of Python, but have you had an opportunity to do so? The link will, let me start sharing a different screen. Okay, I hope you can actually see my screen. So the link there will bring you to this workshop. First thing that I want to point here is that, I don't know if you've seen this before, but we're using here Google Colab. So Google Colab is an online environment provided for free by Google, and it gives you the opportunity to create notebooks like this, where you can mix text and code and execute and run that code without having to install anything on your devices. And it, you know, you can use TensorFlow as well, or for machine learning, and it's all set up for you. Now, in that little, in that notebook, I've added all the information that we really talked about, so that you can go back to it and refer to it after the workshop. But I guess like we could potentially try and run it a little bit. So let's go ahead and connect to an actual live server and go through it a little bit. I'm connected. So the only part that I didn't talk about in the code in the slides was this, but really here what we're doing is we're importing the libraries that we need to use, like TensorFlow, NumPy, and Keras. So we'll go through our first part where we define the model, which is the Keras sequential with one layer and one neuron. Great, and then we're going to define what the model optimizer and loss function is going to be. We're going to supply the data, the x's, which is you know, like I guess the original values, and the y's, which are the answers. And here is where most of the magic will happen, where we're actually going to go ahead and create a model and train it for 500 iterations. So you'll see quite a bit of output here, but it will go very quickly because we only have very little data. And we have quite a powerful machine over here as well. So we pretty much done it. Now here, what we're doing is we're printing like a prediction. So we say predict, and we pass it the value of 10. So what do you think it should give us? So if we say the value is 10, we should be getting back, like 19, as we said before, right? But okay, if I actually run it here, I got 18.98. Yeah. Well, that's pretty close. That's really close to, like you can actually get to 19. You may get a different result actually, although we have the same code. I'm not sure if you run it on your workbooks, but this is literally how we've done it. So you can see we only used 6 lines of code, and we managed to set up a neural network and run a prediction against it. Right? Pretty straightforward once you keep using this repeatedly. So I'll pause a little bit before we go to our next part and see if you have any questions. So when I was talking with Ariel, I wasn't looking at the chat window.
Yeah, Jackie has asked how can we determine the best model to use for our ML application?
So the model is actually what is getting trained. You mean the best algorithms to use, the training and the loss optimizer and the optimizer and the loss. So we'll see in the next. You probably will have to experiment. Actually, I was trying to go into into more in-depth thing, but you can try different things. One thing to look at here. Let's go back into our workshop. The one thing that we defined here, right, is the stochastic gradient descent, right? And the SGD is probably like the best for going through linear values. And then we said that we care about the loss function to be mean squared error, which means like approximately what it would be. When we go to vision, we see that we're going to use a different version of an algorithm in order to do that. It basically depends on the data that you have. And if you go into the TensorFlow documents, it will pretty much tell you what the best is for the type of work that you do. It wouldn't make much sense for a vision scenario, for example, to say that we want to use a gradient descent. I know I haven't really fully answered it, but we'll have to go into quite a lot of detail. I'm happy to share, I guess, links to the documents to see which ones are there, which are readily available in TensorFlow. And as we go through our examples in this and the other workshops, we'll explore a lot more of them. But I would highly, highly recommend using Colab, like here, and both this notebook and the other ones that we're going to use a bit later, in order to experiment with it. So go ahead and change it and see what happens. Any other questions? Clear as mud? Okay, cool. All right, let's try and do something a little bit more interesting. Let's go back into our slides. And actually, these links I'll be sharing with you later, so you can go ahead and save this locally to your local drive or to your Google Drive if you like, and you can feel free to experiment with the entire notebook. Feel free to alter it, change it. I'll make sure that those links will stay active for you. So let's try and go to do something a little bit more interesting, right, with computer vision, and we'll still do it on a on a very high level. Any guess of what this is? This is actually the Google emoji icons. So computer vision is the field of having a computer understand and label what is present in an image. So if you look at this slide, when you look at it, you can interpret what the shirt is or what the shoe is. But how would our program do that? One of the ways to solve this is to use lots of pictures of clothing, tell the computer what that's a picture of, and then have the computer figure out the patterns that give the difference between the shoe and a shirt. And that's what we're going to do in this section here. So first of all, we need quite a bit of data in order to train our machine, right? And fortunately, we have a data set called MNIST, which gives us 70,000 images spread across 10 different items of clothing. All these images have been scaled down to 28 by 28 pixels. And usually the smaller the better, because the computer has less processing to do. But of course, you need to retain enough information for it to be recognizable. If you look at this slide, for example, the quality is not great, but you can still distinguish the difference between, like what this is, the shirt and a handbag. And of course, it's quite clear that this is an ankle boot. So the images are also in grayscale, so the amount of information is also reduced, and each pixel can be represented in values from 0 to 255. So it's only 1 byte per pixel. A bit of math here, but 28 by 28 pixels in an image gives us 784 bytes in total needed to store it. So what will handling this look like in code? Well, we'll look once again at defining a very simple neural network, and we're going to go a little bit different, but hopefully the API should look a bit familiar. The one big difference will be in the data. Last time, we just used 6 pairs of numbers, right? So we could hard code it. This time, we have to load 70,000 images from the disk. So it's going to be a little bit more code to handle that. But fortunately, that dataset that we're using now is available already within TensorFlow through the MNIST API. So what we really do here is we simply declare an object of fashion MNIST and load it from the Keras dataset. Then on this object, we call the load data method, which will return 4 lists: training data, training labels, testing data, and testing labels. So you may be wondering what is actually this, but normally when we build a neural network like this, it's a good strategy to use some of the data to train the neural network, and similar data that the model hasn't seen before, hasn't been trained on, to test how good it is, and figure out what the accuracy is. So here we have 70,000 images in the MNIST dataset. So we'll use 60,000 of them to train the network. And then the 10,000 that are not going to be used to that can be used later for testing. So this code really just does that. It just gives us, like 4 lists. So for example, the training data will contain images like this one, and a label that describes the image like this. Now, while this image is an ankle boot, the label describing it is the number 9. Can you think why that may be? Okay, two main reasons. Right, the first is that computers deal better with numbers than they do with text. And second, more importantly, it's also because this helps reduce bias. If we labeled it like an ankle boot, we would be biasing towards English speakers. But giving it a numeric value, then it doesn't really matter what the language is being used. So we can, could be English, Chinese, Japanese. It becomes a little bit irrelevant. So let's look now at the code for the neural network definition. So we've done something similar a little bit before, and we just had one layer. Now here we have 3 layers. The first important thing to look at this is the first and the last layer. The last layer has 10 neurons in it because we have 10 classes of clothing in the dataset. So this should always match. So before we were looking, for example, we had 1 neuron because we were looking for a single number as an answer. Now we have 10 possible different types of clothing. So we're looking at having 10 neurons in the end to do that classification for us. The first layer is a flattened layer, and with an input of being 28 by 28. 28 by 28 is the pixels that we had on the image, and what the flatten does is takes that square and pretty much flattens it into a single long array with the pixel values. The interesting stuff happened a little bit in the middle layer. Sometimes it's even called as a hidden layer. So this one we defined 128 neurons in it. Think about these as variables in a function. So maybe we'll call them x1, x2, x3. There exists a rule that incorporates all of these that turns the 784 values of an ankle boot that we have in total into the value 9. And similar for the others. It's a little bit too complex of a function for us to go through it and see the mapping by ourselves, but that's what the neural network actually does. So don't worry if this looks a little bit unclear now. Over time, we're going to use that a little bit over and over, and we'll see how it works. The important thing for now is to get the code working so you can see a classification scenario for yourself. And then you can also tune the network by adding and removing changes. So if we get a change, we'll do that in our next workshop. But for now, let's go back a little bit to the code. You'll notice that there are things on here called activation functions. Usually, if you go to the documents for this, you see a lot of math explaining what they do, but I prefer to look at them as algorithms. So for ReLU here, it's basically return the value if it's greater than 0, otherwise it turns into the 0. All it really does is getting rid of negative values. So in the case of our neural network, it's just keeping things simple by only passing a 0 or a positive value for each calculation. Softmax is a little bit similar. In this case, your result is an array of 10 values. Each of the values has a probability for the class. Just to clarify it a little bit for that, we will say that it is 10% probability it's a cert, but 80% probability it is a boot. Right? What the softmax would do is we'll pretty much zero out the smaller values and we'll convert the biggest value into 1. So here in our last entry, which is 97% literally, converts into 1, all the rest of them are zeroed out. So it's easier for us to figure out what the biggest value was rather than going through the entire responses. So time now to compile the neural network just like before. As you can see, nothing really changes. We specify a loss function and an optimizer. And goes back to your question before, the difference is, the loss function now is a categorical cross entropy. Where the keyword here is categorical. So before we tried to before we try to just like go through linear regression, now we try to categorize something, and like what category is it of clothing it is. And the Adam optimizer is an updated version of the stochastic gradient descent that we saw before, but it works better now for image classification. You aren't really limited to using those, but feel free to experiment, change them, as I mentioned before, and go through the documentation to see which of those optimizers and loss functions we have available. And then we actually do the fit, just like before. We give it the set of images and the known labels and ask it to fit one to the other. So figure out the rules that give image 1 label 1, image 2 label 2, and so on. Running for 5 epochs won't give us the best result, but because we have a lot of data, it will move very quickly with us. And we can experiment with that later. So 5 only iterations for getting the result or guessing the result. So we pass in the list of test images and test labels in the end to evaluate the method, and it will classify each one of them. We'll see the predicted results and then compare that to the actual node results, and that will allow us to calculate how accurate our model is. If you want to classify images, you can do that with the predict method as before. Note that you train with with the training data, but evaluate with the testing data, as we said before, right? And it's a little bit about trial and error. Epochs determine how many times we will try. So moving on really quickly, but here's an opportunity again for us to go into another workshop and try it hands-on. I'll stop sharing and try to share that as well. And before we go, I guess, into the, I know that there was quite a lot of mention, obviously, from math of different functions. The code may look a little bit more complicated than before. So if you have any questions before we jump into the workbook, feel free to try and answer them as much as I can. And once again, within that within the Jupyter notebook, I have pretty much reiterated everything that we have seen before. No questions? Was it really clear, or was it a bit too complicated?
Patrick, do you mind sending the link on the chat as well?
Oh, sure. Oops, sorry. I'll have to type it because I don't have it. Go back, stop presenting, go back to the slide for a sec, just in case.
You mentioned having the training set as well as the testing set, but does TensorFlow need to have cross-validation sets as well?
So it's not really TensorFlow that actually needs it. It's something that we need ourselves. How do we know that our model is doing the predictions correctly? We have to have, we have to have both the right questions and the right answers, right? Just like before. Before, in our first example, for example, we knew that what the formula was. So it didn't really matter because we knew the answer would always be 2 times x minus 1. But in case of an image, how would we be confident that when we ask a question and say, classify, for example, this image, and it came back with an answer of cert, how would we know, unless we had similar data that had the answers? And that's the reason why we have, like the testing data, because then we know how good it does against the label that we have at that point. Of course, otherwise it will be too manual of an exercise, right? You have to upload manually an image and say, what I've given you, what is the probability of it being an angle? But that is too manual and too slow to happen, especially when you're working with a large data. That's why we spread it up like this, because then it allows us to get the result across a large volume of information, as opposed to one thing at a time. So yeah, it's not really a TensorFlow requirement, it's a requirement for validation in general of most of our models.
Yep, thank you.
Okay, let's switch back into the workbook. And do you want me to run you through it, or are you happy to go through it yourselves? Is the first question.
Yeah, I think it will be better if we run through it.
Yes, I'm happy to talk through it as I click through it. But yeah, I think it will make a lot more sense if you take a little bit of time to try it out. And I'll try it out. Like I'll just be in your ear, slowly. There's quite a few exercises in this work group as well. And I'll do the first part. And we start again by importing TensorFlow. We import our dataset. Then we break it up into the 4 lists that we discussed about before. And this part is a little bit interesting, right? What we can do here is we can have a look at how the data looks. So remember how we said we used a function called flatten, and we took one of our original images, like the pixels, and converted it. So for the angle boot, this is what our machine looks at. So 0 means like there's an empty pixel, and there's a pixel with, like that kind of like a gradient here, that kind of gradient here. So now the angle boot is being represented by a value for each of its pixels in the image. Right, and you'll see that all of the values here are between 0 and 255. And what we do is like this kind of like there's a process here called normalizing. So we design the model as before. So normalizing would just give it values again, like we would flatten it even more. It would be like between 0 and 1 to make it more simple. And then we define our model with our 3 different layers and our algorithms here with the ReLU and the Softmax. And we compile it. And our training is done, and then let's do an evaluation based on the test images that we have and the test labels. So, okay, so we got back, I guess, like a loss function of 34, like 34, and, like our accuracy is about 0.87. It's about 87%, 87.2% accuracy. Did everyone get up to that level? Okay.
I'm not sure if this question has been answered, but is the loss function the same as the cost function?
The loss function that we're using here?
Yeah.
The loss function is different than the one we used before. It's a sparse categorical cross entropy. Because again, we're trying to, we're actually looking at categorizing each and every one of the images, right? So we want to pretty much give it almost like a percentage of accuracy based on the specific label. I think it was in one of the slides before where it pretty much just went ahead and calculated. Well, actually, we'll see it further down in the exercises. We'll see how that looks.
All right.
So, for example, if we do like classify that in the first exercise here, can you guess what these values are? Is it a random thing? Is it the first 10 classifications that the computer made? Or is it the probability that this item is each of the 10 classes? I know you can see it because the answer is right under there.
Yeah, it says the last one.
Right, the correct answer is 3. So literally, this is really the percentage of the probability that the computer sees of the image that we provided to be on each of the categories. So a shirt, a handbag, thing, and of course, like the highest one of all, right here, was prediction number 9, which means that this is an ankle boot. So as you can see, the percentage was different across the probability of it being a different one. So literally here, I almost answered that again. But how do you know that this list tells you it's an ankle boot? It's because the ankle boot is the labeled number 9, and the probability for label number 9 is much higher than the probability of all the other ones. So it doesn't tell you anything with certainty. But it says I'm almost 96% certain that this is an ankle boot, but I'm only 2.5% certain that this is a handbag. And of course, it's up to us to pick up the highest value and use that. I know we didn't actually go through the list with the labels to see which image is represented in which of the labels. We only focused on the ankle boot, which is the last one.
So how much percentage do we need to know that the prediction is accurate? Is it more than 95?
So 2 different things, I guess. When you do a prediction on a specific item, you'll always get a probability level for that item. So for example, if we gave it an image that, I don't know, we never trained it before. Let's say that from the 10 items of clothing, we didn't have a tie in there. And we provide it with an image of a tie. It will come back with a very low score across all of them. You will probably still go ahead and pick up the highest value. So you will say, okay, the highest value is almost like 2.5% certain that this is a handbag. Well, is that good enough for you? If the highest value that it returns is only a 2.5% probability, then in your code where you actually consume your model, you need to handle that and probably come back and say, well, actually, not sure what that is. Because none of the probability outcome for this image was high enough to give us enough confidence to say that this is what it is. Now, if the question is what is a good amount of confidence, it depends on your use case. Like if we're talking about images like this and we're doing something like, I don't know, in a website or a blog, 75% good enough. But if this is a mission critical application, right? If we talked about medical imaging before, then you're probably looking at very high level, I guess, probability into your outcome. Otherwise, your result is inconclusive. And also, I guess, to tie it back with the other thing, for when we did the training, we got back, 86%, I think, accuracy across the test set. So it said, on average, I'm predicting, on that data, about 86% accurately across the board, like as an average, right? It's also up to you again to decide whether that is good enough or whether you need to start tweaking the optimizer and the loss functions in order to get a better result, or if you need to provide more data and more labels in order to get a better outcome. But there is a risk here, and I'm talking while you're concentrating on your exercises, but the risk here is like there's something that is called overfitting, which means that you've actually trained the model into, to a lot of data. So it's really, really good at predicting things that it has seen before, but then it's going to do badly in things that it hasn't. So there is a little bit of a balance, right? Don't be too, if you have a model that returns kind of like 99.9, success, okay, we probably would start again. It has become like too familiar with what it actually is, with what you're constantly training it on. We made good time. We finished like in under an hour. So you know there's exercises at the bottom further down as you go to that. I haven't given you the answers. And I'm going to be really mean and not give you the answers and let you find them yourselves. Or I can give you the answers in the next one.
Yeah, so if anyone has any questions, just feel free to unmute or type it on chat.
I don't know if you've reached that level, but a couple of them return errors, and the workbook actually explains, the notebook explains why that error is. I don't know if you've hit that point yet. But yes, you'll see a couple of them fail, but that is deliberate. So I guess in the example that I'm running now, the point that it's kind of like trying to make is that you can increase the size of your neural network, right? It probably will increase accuracy, but very little. But the time to execute it, is kind of like, it's going to be much higher. On this kind of like data set. So there's a fine balancing act as well, right? Of how long do we actually train, how many iterations do we take in order not to overfit the model that we talked about before. So running more epochs or more iterations is not necessarily always the best answer. Now on exercise 3, we actually go ahead and not flatten the layer. And you're going to come back and see an error right here. And this is simply because it is expecting the images to be flat of the 28 by 28 pixels and tries to fit this into a 28 layer, 28 layers, 28 neurons. It won't be hard. It will be impossible to do that if we don't flatten the data. And of course, I think I mentioned that a little bit before when I was describing the neurons, because we're trying to categorize 10 different types of items. If we have only 5 layers in the end for the output, you'll still get an error here because basically it just can't fit it. There's not enough neurons in the last layer for all the categories that we are testing. Exercise 5 is my favorite. This is what I was talking to you about before. Sometimes we see like really big, really large, very complicated neural networks, right, with multiple layers. So what actually happens if we do that? So here we kind of like we went from 3 to 4 layers. We added another layer right here. With another dense layer with 256 neurons. Has it really made any different? Do you think it will make a big difference in the outcome? And the answer is, it's going to take a bit longer, obviously, because we have a bigger neural network, but it also depends on our data. We have very, very simple images, right, that we're actually using here. So producing a much bigger neural network with more layers is not necessarily going to have too much impact for us. If we're doing something a little bit more complicated, where we need to keep providing filters behind it, then yes. How do you decide how big your neural network needs to be? Again, like experimentation. So you'll find that when we talk about AI and machine learning building applications, a lot of the time is actually spent on collecting the data and labeling the data, because having good quality data is really important. And there is a large amount of experimentation that will happen when you produce a model. The actual training itself, as you can see, it's not really that big, unless your data is humongous. This protocol will take a little bit of time. So one of the important things to look at here, I guess, as this is training, here you can see the percentage of the loss, right? It started from 26, 11, 7, 5, 4, 3, 2, 1, 1. See how much it's actually dropping now. So at the beginning, you kind of have a really big improvement on the percentage of accuracy of the of the loss. The loss is becoming more and more. But see down here, actually, like now we went 35, 45, 36. So just more iterations don't necessarily always mean better outcomes. And I will leave you with exercise 7 and 8 for you to experiment and try to figure that out on your own. Anyone had any issues so far? Any problems? Anything unexpected on the workbook? If not, I'm happy to stick around, a little bit longer, answer any other questions that you may have. But I'm not giving you the answers for exercise 7 or 8. It will take away the fun.
So for exercise 7 and 8, it's asking us to debug the code.
Mm-hmm.
All right.
Yeah, I'll run it. And you will see that at the end you get a different result. But I guess the question is, why do you get a different result? I will probably ask you to, to like pretty much just go back to the documentation and see why that may be. But what, like I guess the key here is to read up a little bit on what it actually means to normalize our data. And the exercise 8 is what I described a little bit before, where we said that, like we got to a good percentage of like the loss decreased quite a bit, and we've already kind of like reached the level of the desired, like I guess accuracy, or do we need to still continue training? And that is more of like a coding or a Python exercise. And I'm not sure how far you went into the into Python programming, but basically what we're doing is we're using a callback here. Events that we're actually going through the training. If we reach a loss that is less than 0.4, then we kind of like exit the training. But for 7, it would be good to go out and look at the answer yourself. So as you can see here, we actually defined 5 epochs, but we reached our desired outcome after 2, so we stopped training. No need to spend time and energy, or like I guess like processing power doing that. Was that talk, like this little workshop useful? Did they demystify some things for you? What did you think?
Yeah, but for me it's just a bit confusing.
Which the part for the computer vision, I guess the first one probably, I imagine, was it the first part as well confusing, or just the second part?
Yeah, just mainly the second part, because it's more of neural network.
It's not so much more the neural networks, it's more that we're actually diving into something that is a little bit new for us, right? Which is actually, I guess, like expressing an image into pixels and converting that into data, into an array that the machine will look at. And of course, obviously, we use different algorithms. Go through the I guess the notebook once again. Read through it. I'll share the material as well for a lot of those things. And I guess what we can do is in our next workshop, because we're going to try and do something a little bit more complicated with computer vision, to delve into that and try to classify some nice beautiful images. We're going to go into a bit more depth. So it's actually quite normal when you see concepts for the first time to feel really foreign. But what I would like you to get out of this, at least, is that, one, we don't have to write a lot of code. We don't necessarily need to know a lot of math. TensorFlow, and especially with collaboratory, we don't even have to set up an environment. We can experiment pretty quickly with data, and it only takes a few lines to even, we actually essentially we built our own model, right? Very, very simplistic, but we built a neural network here. And we managed to do predictions within a few lines of code. The complexity comes on how you represent the data and what type of, optimizers, what type of loss functions do we need to use in order to achieve that. In our next examples, it will be a bit more fun and more interactive because we get to do something on the browser with TensorFlow.js, and we'll delve in a little bit more into computer vision as well. And if we get an opportunity again, we're going to introduce more concepts, like we're going to go back and potentially do something with speech, or my favorite, which is the generative or adversarial networks, like do something creative. But I hope this was a good introduction, and if anything, yes, you'll have questions, but I hope it almost highlighted that it doesn't take too much to start getting familiar and experimenting with it. And again, I guess obviously this has been recorded, and I imagine some people may see it a bit later. If you have questions about, some of the things that we presented now, or if you need a bit more information, we can always pack it and address it in another session. So do capture those. And I think that's it for me.
Oh, is this the last exercise?
That's the last thing. Yes, we went through it. That's all I had prepared for today.
Yeah, I have questions. So first question is, how do you think TensorFlow can compete with PyTorch moving forward?
Good question. So they're both very similar, to be honest. Things that we did right here with TensorFlow, we can actually do with PyTorch as well. I haven't used PyTorch too much. I think the difference, I know that PyTorch, from what I hear from colleagues in, in my industry and from our community, is that PyTorch is a little bit more popular in research. TensorFlow is a little bit more popular in industry, or in a professional environment. The main differences between the two tend to be between, the ability to publish and release models. TensorFlow has, we'll explore later, has TensorFlow Lite API. That is a little bit more mature when you try to build applications that will do machine learning on a mobile device. We'll explore TensorFlow.js, which PyTorch doesn't do, doesn't do as much. And of course, then when it comes to deploying those models, TensorFlow also have built-in ML ops, machine learning, operations thing for deploying them and running them into the cloud. So, but it's really a preference, right? Some things will be more appealing in the industry, some things will be more appealing to researchers, but both the frameworks are competitive. And I wouldn't suggest go the one or the other. Yes, I may be a little bit more biased to be familiar with TensorFlow, but I would probably say explore both of them and use both of them. And there may be cases where you prefer to use one over the other. It's not that one is much more advanced than the other or way different from the other. It's really good to have both competent frameworks out.
Yep. Yeah, so how would you determine the best machine learning model to use?
For what purpose?
Yeah, for example, in general.
So the model like which we talked about, right? We're using machine learning models for different model or framework, sorry. Because model is literally what we actually create and train ourselves, right? So most of the time, we're either going to go ahead and build something ourselves, like the way we did here now, or in other scenarios, we may use readily available. So if you go into TensorFlow Hub, you'll see there's a lot of pre-trained models, machine learning models that we can start using or extending ourselves. We don't necessarily have to, get one. But what classifies the better, I would probably say it depends on the type of application that you're building and which one will give you the best results. Yeah. It's not, so it's not really, this is better for this. It will really depend. Some of them perform faster. So when you do things like on the mobile devices, we said, or on the browser, you want models that are more lightweight, that don't take too much processing. If you're running something and you're running like very sensitive predictions on like on the cloud, then you may get a more heavy model that that may be able to give you more accuracy, I guess, on something. But it always depends on what your application is. In terms of framework, like when would you use TensorFlow or PyTorch, it's really a preference. Use whatever you're most familiar with, as long as it gives you the results that that you want to get. That's great.
So for
it's almost like asking which.
Yeah.
Sorry, go.
Yeah, this one is different question. So, what were you saying? Yeah. So, next question is because the second activity is applying neural network, but like how would backpropagation apply to this?
What do you mean by backpropagation? Also, you mean like kind of like how would you actually go about about retraining your model by providing it feedback?
Yeah.
Yeah, so I guess like that gets a little bit more complicated, right? In this scenario, we won't be able to do that. We probably have to, because we built it in a very simple way, right? It's not really something that we have built in a feedback mechanism. Most likely, if we take this approach, it means that we need to collect more data and then extend upon the existing model. When we go to our next, potentially, or the one after workshop, we'll look at things like potentially like transfer learning, where we can take an existing model that has like some learning capability and then start adding capabilities on top of it. But yes, I can try and think of an example where we can provide feedback, but that would be way too complicated at this stage. But two ways, yes, either manual, so we go ahead and extend the training, or with built-in mechanisms. And TensorFlow has APIs to do that. You can look at them later.
So do you have other recommended resources where we can learn TensorFlow aside from Code Labs?
So yes, I can share with you a list of books if you like, and of course there are other online courses as well that you can do. Coursera has really good courses from deeplearning.ai if you're keen to dive into those. And there's a series of really nice books that tackle every different API. I'll share the links with you actually. I guess like after this talk with the rest of the material. I highly recommend. Code Labs are good because they give you hands-on experience, but they don't go into too much depth, obviously, with that information. Of course, the Coursera courses will do that for you. And the books, of course. But I highly recommend experimenting with things. When you start, going through a book or through a course, the best way to do that is by taking what you've just learned, even like with these little code labs, and try to, find another data set and try to train a model on it and try to do your own prediction. Because that's the best way, I guess, like getting hands-on with the framework itself will give you a lot more value than diving into too much theory at this stage. Because what we covered it already, it's kind of like very high level, but we're still going to follow the same approach. You're still going to have to collect your data, slice it up, build and train the model, the neural net as we defined, with the layers and the neurons and the output that you want, and train on it. All you really have to do is you have to try it on different data, try with different functions, I guess, for doing the analysis. And try with, I guess, to do a couple of different examples, which we'll try later, not just image recognition. It's what helped me, I guess, when I first started, because as I said, I couldn't find a lot of material readily available. in order to learn, but like getting hands-on with the with the framework itself, it really helps. And if you think about the thing that I like about TensorFlow, it's really just an API, right? It's a framework. All you really do is you consume it just like any other application. Like we just saw it like in our little examples here, right? You just call a function that says feed, or you could call a function that says like with the carrier say load data. So everything is kind of like, as you're going to go through your normal programming, you can start using TensorFlow to do that, as long as you understand the concepts and you have obviously your right data and the outcomes that you want to do. You can keep experimenting.
Yeah. So
to begin with.
Yeah. Can you tell how you did you start learning TensorFlow or machine learning?
It's pretty much just like that. I started myself like doing the same thing. I just jumped into the initial collabs and then start going through the documentation for TensorFlow itself. And then what I try to do is I try to work on little examples of my own. Since my background is in mobile development, I started trying to build and train a model that would do things on the mobile device. So for example, we looked at image recognition here, image classification, but we did that on the, on the browser, right, on the back end. I tried to build something that will run on my mobile device where I would point it to an item and I wanted it to recognize that it is a banana or a phone or a pencil. So looking out for available data out there using those data sets, then I started implementing it into the medium that I wanted, whether it was the website or the mobile app. Start using pre-trained models, which we'll look at our next example, and extending on those. And I think that this is the best way to start feeling a bit, productive with the framework itself and feel like you're doing something meaningful, because you get your, an app on your hands, or on your browser, where it gets to do something that it couldn't do before. So I didn't dive deep, and I still haven't done that a lot into, into the math right behind it. I didn't go through the entire TensorFlow documentation to try and understand each and everything. I only picked up things as I needed them for my purpose, because the subject in the whole area, even TensorFlow as an API, right, as a framework, is really big, and you'll find that many people tend to try to specialize in one area. So find an area that is interesting, that's interesting to you, whether it is computer vision, whether it is speech recognition, whether it is the creative part with generative adversarial networks, and start experimenting with those. It's the best. And then start delve out a little bit. There's no silver bullet. Time with it and experimenting with it, just like anything that we normally do in in software development. Try to do something, get hands-on with it. I promise it becomes clearer. You just do things later.
Yeah, so this activity is for computer vision, but can you explain a bit of photo OCR?
So it's a different thing, right? Actually, OCR. We can do an exercise later down the track, or I can share it with you. We can do something like handwriting recognition. But the concept is really pretty much the same. We still get a lot of data of of letters and numbers. We label them, and we train the model using literally the same thing, because we still feed back an image. It's just a matter of training it on a different data set in order to give us higher level accuracy on figuring out what that letter is. Which is literally what it says. It's literally, rather than trying to classify it as a boot, you try to classify it as a character. So it's the letter A, letter B, letter C. I would probably say that you have enough here to pretty much try it out yourself and try to create something that will recognize a few characters. All you really need to do is get quite a few images of handwriting, or I'll search some of those with you and you see how it performs. similar concept, different data.
How can you determine how much data do you need for the application?
Good question. The more the better. I say, you can never have too much data. I guess you have enough when you after you finish training and testing, you're getting the outcome that you need. So once you finish going through the process that we went through, if you're getting back an accuracy that is good enough for you, then I imagine you have good enough data. Otherwise, you need to go out and get more. And that is where the most, I guess the most difficult part of it is. Maybe I don't know, depending on how many sessions we're going to do, depending on how many workshops and the appetite that you have, we maybe later down the track we'll look at things like Kaggle, where it hosts quite a lot of different data sets that are quite large, and we can then start exploring some of that data to build models. But I guess even from an industry perspective, you'll find that most organizations really focus on that part. It's a lot of work is about collecting the data first of all, cleaning it up, make sure that it's good quality, and then utilizing it properly. I worked in banking before I was at Flybys. A lot of data, very difficult to go through it and clean it up. So a lot of data scientists, if any of you want to get into that field of machine learning, data science, especially data science, your time will be spent just literally collecting, classifying, and transforming data in order to produce something really useful. If machine learning is the thing, it's more of an engineering task, I guess, because you get to deploy models into production, allow consuming from an application perspective. But yeah, that's almost like the last part of the equation. And there's different tools that are being used outside of TensorFlow. TensorFlow is good, not so much for obviously for manipulating data and collecting it. It's more better for training the models and deploying the models, as we will see later. There's lots of work to happen beforehand.
Yep. Also, I know that machine learning is mainly part of data science, but then do you think it will be integrated with software development in the future?
I think it already is. A big part of data science is already, if you think about it from a software engineering perspective, a big part of data science is that. You'll find that the terms are being intermixed a little bit in industry at the moment. You probably won't see a lot of ads for machine learning engineers, but you see a lot of ads for data scientists. And data scientists tend to go almost like two paths. Some of them that are specializing on actual data and getting insights out of the data and manipulating it. There's some of them that spend a lot more time on the engineering side of things, like on TensorFlow, right? Training models, or even on data engineering, where then go ahead and deploy the models. Machine learning as a term sits in between the two. Almost like now, where you probably need to understand the data that you have from one perspective, and then train on it in order to create a model. But then, of course, we tend to just go to the engineering side of things and deploy it, whether it is cloud or on-site. So you'll find it's not really, what I'm trying to describe is literally not clear cut. You would think that data scientists spend a lot of time with data and try to collect insights, but it's not always the case. And machine learning by itself is it's both an engineering task and a data training and manipulation task.
Yep. So I guess that's all the questions I have.
Oh, good.
Does anyone have any other questions? Yep. Okay. If not, then I'll go with the wrap up. Oh,
awesome.
So yeah, so for now it's the wrap up, and so what's gonna happen next. In the next month, we're gonna have a hackathon called Hack Vision, and it will be held on the 20th and 21st of November. So feel free to register on our website. I'm just gonna send the link on the chat.
That looks so cool. Can I join you?
Yeah, so the hackathon will be a 24-hour competition, and it will be a good opportunity to form your team and create an innovative solution for a specific problem. Yep, so I sent the link on the chat if you want to register. And here are social media, so you can join our Discord or subscribe to our YouTube channel and also follow our LinkedIn. Yep, so if you want to connect, just scan our QR code and yeah. Also, I can send the links on the chat as well. Yeah, and then thank you for attending, everyone. And also thank you Patrick for being our guest speaker for tonight. And
no, it was my pleasure. Thank you so much for having me, and I hope we, after you finish with your exams, we'll get to, have an opportunity to do a few more workshops and do something really, really fun that you can actually start sharing around and playing with.
Yeah, I'm looking forward for having those workshops as well.